Thank you. A warm welcome to this talk. Actually, with 500 string theorists, we have been here for a week studying the latest developments, and you can imagine we really are looking forward to a drink. And so this is a very special audience, because I would say like 1 in 4 among you are real specialists. So for the others, the trick is to find the string theorists and in the break or over drinks, ask them anything you want them to know. So the topic tonight will be about a very an object, a subject that's just around us: space and time. Now, if you think about space, actually the stage here is a good metaphor. For many, many centuries, people thought space is just out there. It's flat, it's rigid, it's forever as it is. It's just the background, the decor in which natural phenomena happen. And time, similarly, was just a big clock that directed all the phenomena that happen in nature. And as Newton famously said, it's an absolute and time that kind of goes on forever and ever. It flows without regard to anything. Now, all of this changed dramatically with the next character, Albert Einstein. Now, Albert Einstein famously said, time is the 4th dimension. And we'll be talking tonight about extra dimensions. And this might be something a little bit dizzying for you. So let's start slowly. So let's start with 2 dimensions. Now, we can all imagine this is a square. It's actually nice, 2-dimensional. Let's go to 3 dimensions. Oops. This is 3 dimensions. Actually, this, I hope you appreciate my PowerPoint presentations here. They're homemade. So this is a cube. But actually, you're not watching something 3-dimensional. Of course, this is a 2-dimensional screen. But even if I would have brought a real cube, right at this moment, you're looking at your retina, the back side of your eyes. And so if you think you see the 3rd dimension, actually it's an illusion. Your mind sees the 3rd dimension. So why not go 1 step further and, for instance, try to see 4 dimensions? This is a 4-dimensional object. And I had a colleague who looked at these objects for a full year, manipulate them in the computer, hoped that something would say click in his mind, and he would see the 4th dimension. That didn't happen. So I'm always looking for a volunteer that spends a little bit more than 1 year trying to do these exercises. But actually, this is not even what we're trying to do. I want to actually explain this with another example. This is a little movie. So you see 2 little balls moving, but actually you're not looking at the movie. What you're looking at, as in any movie, is a sequence of images. So think of the individual images of this movie as individual pictures and stack them up in a high stack, like this. You see, if you go up in the stack, you're later in time. Time is flowing upwards. So we have 2 space dimensions and 1 time dimension. Well, Einstein said, is let's glue all these little things together and make one big thing, call it space-time. It's the one on the right. And you see the little balls are now these kind of spaghetti strands that go up. So while we are sitting here in the stage, we are moving in space-time. We are moving in time. All of us go like 1 second per second, flowing up in the 4th dimension. Now, of course, whenever we talk about physics, I'm kind of lying, because the real thing is showing the equations. Now, I know if I'm showing equations, it's very dangerous. But you know, you shouldn't be afraid of equations. Now, a typical equation looks like this. A equals B. And the most important part of that equation is actually right in the middle. It's an equal sign. Good equations connect 2 worlds, A and B, that you might not have thought are connected at all. And so, for instance, Einstein was brilliant in writing these kind of equations. For instance, the most famous equations, I think, in the world is the equation E equals mc squared. So if you think about that equation, let's try to see whether I can produce it. Yes, there it is. Why is it such an important equation? Because it connects 2 different concepts, energy and mass, in a way that you might not think are connected, with tremendous consequences. It means you can take mass and produce energy out of it, as it happens in nuclear processes and atom bombs. Or you can take energy, pure energy, and create particles out of it. That's actually what happens in the big colliders. Now, there's a similar equation that is even more powerful, which is the equation Einstein used to describe gravity, general relativity. Now, unfortunately, this equation is not as famous as E = mc², it's a little bit more complicated. But it has the same kind of beautiful flavor, that it connects two worlds that you wouldn't expect to be connected. On the left-hand side is a mathematical symbol that captures space and time. On the right-hand side is something that captures mass and energy. So in words or in images, what this equation is doing, it's telling basically mass tells space how to curve. If you put something in space, like I'm standing here on the stage, actually it's like the stage is made out of rubber. It will bend. Space can curve, space and time can curve. That's one part of the equation. And reading the equation the other way around, it says space-time tells mass how to move. Because if you have a curved space, what do you mean even by going straight? So for instance, if you think about the moon orbiting the Earth, actually it's the Earth's gravitational field curves the space around it. And the moon tries to go as straight as possible in that curved space and has this beautiful circular motion. Well, this insight of Einstein was absolutely brilliant. And he realized that if this is the case, everything should actually curve. What happens here? Yes. Everything should be curved, in particular also light. And so he proposed an experiment to measure the deflection of light of stars close to the sun. And this could only be done after World War I in 1919. In fact, last May we celebrated exactly 100 years ago at the eclipse of May 29th, 1919, that this particular experiment was done by the British astronomer Sir Arthur Eddington. And he actually measured this and created this wonderful picture. Here you see it. Oh, here you see it. The solar eclipse. This is actually a copy of that picture that we have actually in Princeton. It belonged to Einstein. So this actually showed him he was right. But this was just after the war. He couldn't directly communicate with the British. And in fact, the communication went through the link between Einstein and Lorentz. Lorentz, the famous Dutch scientist. Here they are together. And so Lorentz had the honor of informing Einstein that he basically made the biggest discovery in science. And here is the telegram, and it's kind of funny because it writes, Lorentz is very Dutch. So he writes, okay, Eddington found the star shift at the solar edge, preliminary sights between 0.9 seconds and double, Lorentz. So nothing like, congratulations, you just made the biggest discovery in the world. Probably you have to pay for every word. But of course, this was not the reaction of the press when it finally appeared. There was this wonderful headline in the New York Times saying that stars were not where they were calculated to be. Nobody needs to worry. Also this book of 12 wise men, which is really, I think, ridiculous. And in the German press, he immediately was celebrated as a new giant of world history. So instantaneously, Einstein became world famous. He traveled all over the world, including to the United States, to New York. Here he arrives.
The greatest scientist of Germany in the greatest city of the world. I'm delighted.
I'm delighted.
What do you think of prohibition, Professor?
Ich trinke nicht, also ist mir das ganz gleich.
Professor, freut es Sie hier in Amerika wieder zu sein?
Wenn ich Sie sehe, sicher.
A wonderful clip, and he would definitely not enjoy the cocktails. So, of course, as I said, Einstein was then in a wonderful position. And he could do, for the first time, a calculation people only dreamt about. He could actually put the whole universe in his equations. He could calculate what happens to our universe. And he made a tremendous discovery. He found that actually the universe wanted to expand. And this was really shocking, because he immediately realized if it's expanding in the future, then in the past it must have become smaller. And there must have been a point, what we now call the Big Bang, where the universe was created. And this was so strange, the fact that everything would be created at a single moment, that he did something very bizarre. He changed his equations. He actually added an extra term to his equation. We call it now the cosmological constant, a mysterious force, he presumed, that's in empty space, that is kind of helping the universe to stay in place. Afterwards, and now we all know that the universe does expand, he must have said that this is his biggest blunder. But because he was in a position to predict, perhaps the greatest prediction ever, that we live in an expanding universe, and that there is a moment where the universe was created. That moment actually came later, and in fact it was the Belgian physicist Georges Lemaitre who actually made that discovery. He made this prediction in 1927. He's a unique figure. He was also a priest. So he was the one person, Einstein and the Pope were one handshake away, and that was actually Georges Lemaitre who was the in-between. I think the only thing he wasn't successful is in naming the Big Bang. He tried primeval atom, cosmic egg, and these names haven't stuck. I think they're quite beautiful. In the end, it was Big Bang. The actually astrophysical detection of the expanding universe was 2 years later by the American astronomer Edwin Hubble, who actually noticed that the galaxies were kind of floating away, were moving away from our Milky Way. Now, this is something that we're now familiar with. An expanding universe is like the universe is a big balloon that's being blown up. But you must realize it took a long time for people to accept this idea. And the crucial moment was a measurement made by 2 radio astronomers, Penzias and Wilson, who they were actually just engineers that worked for AT&T Labs and were working on this microwave satellite reception dish that had an annoying noise. And they couldn't remove the noise until astronomers told them, you guys might have picked up the signal of the Big Bang. And it's a very impressive signal, so I think we should all listen to it for a moment. This is the sound of the Big Bang, but 14 billion years after it happened. In fact, you can observe it with your own old-fashioned television set. If you have a television set with an antenna, then there's little noise if you don't pick up a signal. And apparently 1% of that noise is coming from these photons, these light particles, that had traveled all the way through the universe to arrive on your television screen. But in fact, now we can measure this more carefully. This is a beautiful picture here. This is not a pointillistic painting. This is a so-called baby photo of the universe, as it was just after the Big Bang, roughly 400,000 years, but cosmologists find just after, in a split second after the creation. And these little pixels, actually, these little changes, are responsible for everything we see around us. We have now a full understanding how, from these initial conditions, the universe was formed. So if you now look at this little animation, you see, by zooming in, that these little changes, matter is being created. Actually, it's through gravitational interaction, it condenses. The first elementary stars are being formed. The first versions of galaxies, these galaxies grow, the stars grow through many generations. Planets are being formed. In the end, our sun is being formed, the planets around our sun, including our Earth and life on Earth. So we live in remarkable times in the sense that we have a pretty complete understanding of 14 billion years, 13.7 billion years of cosmic evolution. And a remarkable thing, that whole story was figured out by us here on planet Earth in less than a century. We have been able to capture that whole story. So it's a terrible and terrific success. On the other hand, I often joke that cosmologists are special because they know exactly what they do not understand. And many of you might ask, what do I know I don't know? And almost like these old maps. The old maps were made by cartographers. And of course there were empty spaces, there were blank spots on the map. But they didn't dare to leave them open and blank. What they did, they painted and drawn these awful sea monsters. So in some sense, we have still sea monsters, no longer in our oceans, but in our understanding of the universe. And let me show you two of these sea monsters. The first, if you look at galaxies, astrophysicists have found that these galaxies are not just galaxies, they're surrounded by huge clouds of matter. Matter that's invisible. It's actually transparent. We call it dark matter. This dark matter is actually everywhere in the universe. In fact, the amount of dark matter in the universe is roughly 5 times more than the visible matter that we are made out of. So if you could see that dark matter, the night sky would not look like this, but you would see all this stuff. So I often like the example of a Christmas tree at night. So we, that is to say stars and planets and all of us, are like the little lights in the Christmas tree. But if we would be able to see dark matter, we were able to see the branches and leaves of these Christmas trees. If you actually could see dark matter, the universe would look very different. If you would fly through, you would see these big strands of dark matter that somehow hold the whole universe together, where our stars are just these little candles on the branches. There is another sea monster that came as a big discovery. When astronomers were measuring carefully the expansion of the universe, they found that it's actually, they might think it would slow down. You have a big bang, and then in the end, gravity tries to pull things together. But exactly the opposite seems to happen. The universe is expanding faster and faster and faster. It's like that space is like a sponge that has been compressed and wants to kind of expand. In fact, it's the wonderful recurrence of Einstein's idea of a cosmological constant. So his blunder was brilliant. The man is really very special. However, the effect is not what he was looking for, something that would hold the universe together. It actually has the opposite sign. It's making things worse. Empty space wants to expand and create more empty space. And this is one of the remarkable discoveries. In fact, if you look at the composition of the universe, if you think of it as a cocktail, to use tonight's metaphor, only 5% of the cocktail we understand. That's made of the matter and gas and radiation that all physics covers. Here, the physics that we understand. 95% is made out of these two mysterious ingredients, dark matter and dark energy. And so that's progress. At least we know what we do not know. Now, there's another thing that we don't understand, and these are black holes. And black holes have been in physics for a long time. Early after the discovery of Einstein's theory, physicists already realized that if you have a lot of matter put together, then actually stars can collapse and create not only a little hill, a little indentation in space, but really it's like throwing a bowling ball on a rubber screen that kind of creates a real deep, infinite deep hole. Now, we're living in remarkable time because all of us were around on April 10th of this year when the first black hole image went around the world. I think literally every newspaper in the world must have had a picture of that famous black hole. In fact, it was a gigantic black hole. It's a black hole that lives in a galaxy, not our Milky Way, but, let me try to get this. Yeah, measured by the greatest telescope that we ever produced, a telescope literally the size of the planet by connecting individual telescopes. And it looked at this galaxy. It's called M87. It's 55 million light years away. It has a black hole, we thought, in the center that somehow swallowed more than 6 billion stars. And just for comparison, here you see on the bottom left our Milky Way. So, even as a galaxy, we are kind of average, what this telescope was able to do is create an image that is, by the way, the most magnified image. Never ever we have created such a big telescope, and never ever have we seen such a small detail on the night sky. So it looked in this kind of galaxy. It's close in Virgo. Here we are zooming in. You see this big thing flaring out, and here's the image. This kind of black hole. Absolutely remarkable, and you indeed see a black thing in the middle that's very closely related to the hole that the black hole creates. And I must say, just a personal story, a few years ago I was asked to paint a mural for a black hole center in Harvard. So I painted a black hole, and I said, well, if it's actually ever being photographed, I will repaint it. But actually, I think I was pretty good if you look at the image. I think I can even magnify it. Here it is. So pretty good. So. But again, black holes are astonishing objects to understand, because the one thing they do, they have to, as you say, what are you looking at in the middle? This black hole. In fact, it's called the horizon. If a black hole is formed by matter that falls in, it all gets squeezed into a point, but inside or around that so-called singularity, there's a no-go zone, a sphere surrounding this, which we call the horizon. And if you fall through the horizon, you're doomed. And in fact, you're doomed in a very bizarre way. Literally, time that usually in these pictures is flowing upward, inside the black hole, it moves inside. So the moment you step into this black hole, there might be just, like in this particular black hole, there might be just like a few hours of time left. So it's like you're watching a movie and it's still 10 minutes to go, something dramatic has to happen because the movie has to come to an end. This literally time stops. And that's something that we're really worried about. Now, I think of this, if you think of the history of the universe, we have this tremendous success. But there are two things we really do not understand, which is the beginning and the end. How did the universe start at the Big Bang, and how does it end, as it does, inside black holes? So I think it's a little bit like one of these beautiful Flemish tapestries, where at the very edge, you see what the fabric of space and time is made of. And there's a famous scientist, John Wheeler, who said, how can this be? These space-time singularities, how can physics lead to a violation of itself, to no physics? As he said, how could it be that Einstein predicts that this theory is unpredictable? And so we love this. Now, these are the kind of the open problems that we want to solve. Now, I hope you're now thinking of space-time in a very different way. It's no longer a rigid stage. It's very flexible. It's full of life. It can curve, it can begin, it can end. It's a very rich topic to study. But to find really the solution to this, we have to turn to the other direction. Not outwards, but inwards. And look at elementary particles. That's the world of accelerators, where these kind of a big mess is being created by colliding particles. We're zooming in to the smallest structures. Now, for a long time, people thought that, this was unsolvable. Particles were so difficult to understand that it could have been a black box. But then they discovered in the 1970s and later that actually not only the box could be opened, but inside was a very tiny formula. I don't want you to understand that formula, but you must appreciate the power that a single line is describing actually all the physics that you see around you here. The particles that you are made of, that everything is made of, and how they interact. Now, if you actually go and take a physics course, you get something like this, which is the real thing. But I would like to say, you can also put the whole thing on a t-shirt. In fact, now with the Higgs particle, I should say the Brout-Englert Higgs particle added to it, 17 particles that are describing all of physics as we understand it. It's a tremendous success, a tremendous success. Now, how is this theory kind of constructed? And we have to actually go into the world of quantum mechanics. Now, quantum theory is very dizzying, it's very bizarre, but I want to explain it a little bit with one of my favorite kind of metaphors. And that was a metaphor that was created by John Wheeler, when he was a professor in Princeton, talking to his graduate student at the time, Richard Feynman, famous physicist. And Wheeler asked Feynman, how come that all particles, like all electrons, are exactly the same? Now, they have the same charge, the same mass. It's like there's a factory that produces these particles with perfect size and perfection. And he says, I know the solution, because there's only one particle in the whole universe. So what did he try to understand? And there's all the same electron. So was this image. Here's the particle. Now usually this particle has to go up in time, like everything else. But suppose that we could be more liberal, and particles could also backwards in time. So it would be like there's a time machine here. I could step in a time machine, go back an hour, walk inside the lecture hall, and stand here next to me. It would be a perfect copy of me, right? I could do it 3 times, 4 times. I could make identical clones of myself. So Wheeler said, suppose that this particle is able to float through space, up and down, and creates a big knot. That would be terrific, because if you think of this as a movie sequence, you would have a single particle in the beginning. But in the middle, if you would cut it, you would see many particles and antiparticles, that's the particles going down. And of course they are the same, have the same properties. It's the same particle. Well, there's lots of problems with this, and the war intervened, and Feynman forgot this whole discussion. But then in the 1940s, you start thinking about it again. And I love this image. This is an image of his notebooks, where he very, very carefully tries to push these particles backwards in time. And see, how does that work? And it works beautifully. He's able to reproduce, with these diagrams, all of physics. And now, of course, they're called Feynman diagrams. In fact, there's a nice anecdote. A few decades ago, there was a young physics student, and he saw this van driving in Los Angeles. And there was a woman driving the van, and he stopped her at the intersection and said, Madam, do you know these diagrams, these graphics on your van, these are called Feynman diagrams. We use them every time. We use them to describe the world. And she said, yes, I know, I'm Mrs. Feynman. And here's the family with the van. And in fact, the van is celebrated. It actually was recently, you could buy it. So somebody bought it, and I hope it will end up in a museum. In fact, there are many more things here to be said. If I can wake up my computer. Yes. Because if you look at the Standard Model, there's one thing it says, which is these particles. So what a beautiful theory. This is amazing, powerful. But another part of our brain says, why this? Why does every particle come in like a small, medium, large? Why 3 colors? There's a lot of things that do not really make sense. So we try to make more sense of it. We play with these models. We try to combine them in different patterns. Say, perhaps there's a grander theory that kind of unites all of this. And we notice that the forces in nature, there are 4 fundamental forces. They are very different in ordinary life, but if you go to higher and higher energy scales, they seem to be getting closer in character. So we think that nature has a bigger story to tell, and it might be connected to all the other things that we do not understand, the 95% that is missing. In fact, quantum mechanics is a bizarre theory. Not only can you go backward in time, but for instance, this can happen. A particle for a brief moment can split in 2 particles and then reunite again. I like to say, if you do it fast enough before it's detected, it's okay. Which actually fits very well, by the way, with the Dutch attitude towards life. I think many of our laws are based on that. In fact, you can have something like Wheeler proposed. You can have this. You have 2 particles, a particle and antiparticle, being created out of nothing. Or, if you wish, a particle going up and down in time forever and ever and ever. So these things happen, actually right as we talk, in empty space. In fact, this is my visualization of empty space. Empty space and time is filled with these little bubbles of nothing, particles that live for a very brief time, like little fireflies, for a brief moment. In fact, there's a wonderful saying that, like in quantum mechanics, everything that's allowed is obligatory. Everything that can possibly happen happens in empty space. And we think this has a tremendous consequence because this sponge, the fact that space itself has its own pressure, it has its own force, its own energy, must be a reflection of all these quantum processes. In fact, we think that if you look close into space, the analog of a sponge might be right, because if you zoom in, zoom in, zoom in, at some point, like in an ordinary sponge, there must be little pixels. There must be little atoms of space itself. And we somehow know how small they are. They're remarkably small, 10 to the minus 35 meters, called the Planck length. But we do think that in the end, space disappears. In fact, one thing I find absolutely amazing, that we now have an understanding of both the smallest and largest distances in our world. The smallest distance is this Planck length. It's the scale in which space itself no longer makes sense. If you zoom further in, you don't see anything. There's also a larger scale, which is the scale of the universe that we can see. It's the so-called visible universe. It's the Hubble scale. And there are 60 steps of 10, powers of 10, to go from the left to the right. Right in the middle, I find this very kind of metaphorically pleasing, is the scale of life. The scale, say, of a bacteria or human cell. And if you go one step to the right, you actually at the level where the moon is, the distance to the moon. So that's as far as we have traveled as human beings. And if you take a step to the left, you're roughly at the scale where the experiments in CERN, the most smallest elementary particles that we have detected are. Though that's where we traveled in terms of the microscopic world. So this is a pretty amazing picture, that we actually have created this picture and understand this picture. Now, there's one question, I think, that was already raised and that everybody asks, what happened before the Big Bang? And I give you a little anecdote, because I was with my son, who was 8 years at the time, in a beautiful exposition in New York, which was, a simulation of the Big Bang. So we're standing in this dark room, and certainly a big flash, and then we saw stars and galaxies. It was amazing. And afterwards, he said, "Daddy, that was remarkable, but when we were waiting for the Big Bang, what was this?" I say, "Well, that's the question, what's there before the Big Bang? That's exactly what Daddy and his friends are thinking about every day." "Yes, is this true? Wow, cool." So I felt so great with this episode. And so that day, you go to the office with a little bounce, this is terrific, 8-year-olds understand what we're doing. And afterwards, so I came back home, and he looked at me and said, "Anne?" So for a day. But there's a beautiful thought. The beautiful thought is that at the Big Bang, there was a period of rapid expansion, what we call inflation, where these small wiggles that are always part of quantum theory have been magnified in a tremendous way, blown up literally to cosmological proportions, creating this pointillistic painting that the Big Bang started with. So there's a beautiful idea here that, if you want to understand why the universe is as it is, which is understanding the world at the larger scales, we actually have to understand it at the smaller scales. And there's a connection between the smallest and the largest, which is somehow very satisfying. In fact, there are other things that we think we can understand by marrying these two theories of Einstein's theory and quantum mechanics. Famous result is due to Stephen Hawking. Remember, I told you that in empty space, there are continuously particles and antiparticles being created. But Hawking asked the question, what happens if these particles just live on the very boundary of the horizon of a black hole? Then the following thing might happen. One particle is outside, the other one is inside. The particle that's inside is doomed. It's being pulled into the black hole, and the other one has to escape. And through this idea, black holes can, at least on paper, they can radiate. They again kind of emit particles. It's not literally a black hole. It's a slowly glowing black hole that gives back the information. Now, to understand all of this, you need proper physics. And this is exactly the topic of string theory. So indeed, string theory is something, quite simple to explain in the audience. Let's see what happened. It's a generalization where instead of thinking of particles, little points, we literally think in terms of vibrating strings, like here we have in the pianos or in the violins. And if you have a string, it can kind of resonate at many frequencies. It can have many tones, the harmonics of a musical string. And in physics, the different harmonics constitute different particles. So it's one way to unify all particles. And remarkably, one of those particles describes gravity. Now, it has many, many advantages. Like, for instance, you have these famous Feynman diagrams, which describe the standard model. It had many questions for why this. In string theory, these are described by two-dimensional surfaces. And the interactions between these strings are purely geometric. That's actually something we like very much. There are many other kind of advantages. And in fact, there are not only closed strings, there are also so-called open strings. And open strings are strings that have two endpoints and they can be attached to object branes. And if you want to study string theory, you have to study all of them together. And it's a magical mix, it all hangs together, and you can find remarkable results. And I want to present a few of these, just to get you a taste of what string theory can do. For instance, this is the way in which string theory understands black holes. So here's a black hole, the horizon of the black hole, that's the area you shouldn't fall in. And outside are these so-called closed strings. What they do actually, they describe the gravitational field. So they describe space-time at the elementary level. And then there are also kind of these open strings that are kind of attached to the horizon. And we think actually these are the ways to describe quantum black holes. And for instance, one thing that string theorists have done is this, to calculate what happens if you look under the microscope. In fact, what you see is that some of these open strings can attach and fly off. And that's a calculation that reproduces Hawking's result. So in string theory, we have a full understanding of certain classes of quantum black holes. That's a tremendous advantage. In fact, there are other crazy ideas. For instance, there's the idea of holography, that in some sense, it's good enough to only understand that surface of the black hole. That basically, just as you have a hologram, which looks like 3 dimensions, but it's only 2-dimensional, and if you move, you see the illusion of a third dimension. Actually, string theorists think that even the dimensions that we are experiencing every day might have that illusionary element. They might be part of a kind of cosmic hologram. And in fact, that's why we're so excited about black holes. Because if you want to see one place where quantum theory and Einstein are really clashing, it's in black holes. I like to say they are like the atoms of the 21st century. On the one hand, from a gravitational perspective, a black hole is just a hole in space, the simplest possible object you can have. But from a quantum perspective, it's the most effective way to store information. It's like the most compressed hard disk that nature has built. And so we love these kind of paradoxes. If something is from one point of view the simplest object, from another point of view the most complex object, and yet these things exist, we have seen pictures of them in the newspaper, that actually means that there's this homework assignment. We haven't figured it out. But nature has. We know that nature has found a way to marry these two concepts. So we think that you have this dizzying display of scales. We think that there might be even something more fundamental than quantum space-time. That perhaps pure information, zeros and one, or more precisely quantum information, might be something that's underlying all of reality. And people have said this, we might be a little bit like living in the Matrix. Might be all kind of a big simulation. Or in the end, perhaps there are just bits and that's it. There's one final thing I want to bring to your attention. Now, in string theory, there is a need for extra dimensions. And this is actually a very old idea. Einstein himself was very puzzled by this and fascinated. Very soon after his discovery of his theory of gravity, the 3 space and 1 time dimension, people figured out that if you have 1 extra space dimension, so if you have a little circle at every point in space, that would have tremendous consequences because, first of all, you get electromagnetism, and particles cannot go straight, but they can go in little circles in this extra dimension. And depending on the speed in which they go around the circle, they have a certain electric charge. So it's a beautiful example how you could take 2 forces in nature, electromagnetism and gravity, and unify them using an extra dimension. Now, in string theory, we need not 1, but 6 of these extra dimensions. And sometimes we have even models where there are 7. And they can be curled up in much more complicated ways than just a circle. And so we study these theories, these beautiful images here of these manifolds, very intricate ways in which nature would be hiding these extra dimensions. In fact, there's a dictionary. There's a dictionary that tells you that the shape of that space is in one-to-one correspondence with the phenomena that we see in our 4-dimensional world, like the things that were on the t-shirt, the particles and the forces. And in some sense, that is realizing Einstein's dream. Einstein always wanted to produce everything out of geometry. And so string theorists are in some sense trying to realize this, using in the same time also quantum theory. Now this has tremendous consequences, because if the physics, as we realize, is produced by the way in which these internal dimensions are curled up, and this cannot be done in a unique way, there are many choices, there's something, a whole landscape of possibilities. And perhaps now our world, our laws of nature, what we think is something that's unique and picked out by whatever, by God, by nature, to describe the world, might be just a choice. There might be other alternative universes. And if you're taking this serious, you have to start thinking about what we call the multiverse. All possible universes. And it's not a thought experiment, because we think under the laws of quantum mechanics, it's very well possible that one universe can create, so to say, another universe, a baby universe, which has a complete hard reset with different laws of nature, a different set of particles, and perhaps completely different kind of cosmology. So this is absolutely dizzying. And so if you think about, I had an even bigger picture, but there's a yet even bigger picture, where at the other end, at some point we thought, well, the natural endpoint of our thinking is the whole universe. That might not be the end. We might go even bigger. We might live and have to study all these possible universes. So I think this is an absolutely remarkable picture. And I would like to say this is the moment when you arrive, what I would like to say, at a higher level of confusion. It's just the thing that we are struggling with. And often, the one thing that physics does is not so much provide all the answers, science does, but provide these wonderful questions. We somehow start to get to know what we do not know. And I want to kind of finish by 2 quotes. The first actually is by Einstein. And when he was a young boy, there's a story he has been telling very often. He was 5 years old, and he was sick, and he was given a magnet, a compass. And he noticed that the compass needle was always pointing in the north. But then he actually started walking around through the house with the compass. And he realized there was a force pushing, guiding the needle. And that there was something he couldn't see that filled all of the room. Of course, he discovered, as a 5-year-old, the magnetic field. I think it's a beautiful metaphor, because Einstein, in his world, his life as a scientist, discovered that indeed, space is filled with all this magic. It can be curved, it can expand, it can begin, it can end. It's full of these quantum particles. It's a beautiful metaphor. And the quote I want to give you is this one, that he said, in the end, imagination is more important than knowledge. Knowledge is limited to all we know and understand. Well, imagination embraces the entire world and all there ever will be to know and understand. The blank spots on the map, the place where perhaps sea monsters live. But we are so excited to discover. I think in some sense scientists are the equivalent of the explorers of the old days that sailed into the great unknown. The final quote I want to give you is from Stephen Hawking. So as you know, Hawking passed away last year. He passed actually away on March 14th, which is Einstein's birthday. In fact, I think Hawking was born on the day that Galileo died, so there's a lot of cosmic coincidences here. And when he passed away, there was a message from him that was beamed into space using a big radio telescope. In fact, it was beamed in the direction of the nearest by black hole. So It's underway. You know, it has now traveled for 1 light year. It will have a few more days to go, years to go, to arrive there. But I think it's a wonderful idea that this message is still floating around. And I want to play a small clip of the message in that in Hawking's very characteristic voice.
We are all time travelers, journeying together into the future. But let us work together to make that future a place we want to visit. Be brave, be determined, overcome the odds. It can be done.
Thank you very much.